so far is people getting mad enough at these problems to just throw their book right on the floor. Just don't do your calculator. Just don't throw the calculator. So, all right. Let me say something to you right now as far as. So one thing I heard was, how do I know which one to do? Number one, we're going to do use substitution way more than we're going to do this thing, integration by parts. Way more. But there are just a lot of functions to do the antiderivative. There are just a lot of different ways to do them. Some functions need use substitution. Those are mostly ones that have stuff on the inside or have something on the bottom. Stuff on the inside or something on the bottom. That's the stuff we use substitution for. Now that's a lot of functions, okay? But there are functions where that doesn't work for, all right? So the ones where we're going to do integration by parts are more like products that don't have an inside kind of a thing, all right? So they're going to be things that look like this. The one we did, e to the x times x. They're going to be things like x times sine x. They're going to be things like e to the x times sine x, mixture of function families. They're going to be things like x squared times ln x dx. There are other ones, but for our gateway test, they're going to be ones that kind of look like this. Okay? They're a mixture of function families. They're pretty simple in the sense that they don't have a lot of stuff in them. Right? Because the use substitution ones are the ones that have a lot of stuff in them usually. Like yesterday we gave an example that if this had e to the x squared, then it'd be a use substitution because we let u be the inside. It has an inside. None of these really have an inside. Right? The only thing on the inside of anything is x. So if you see something like that, that's integration by parts. Now in the homework it did get into some pretty tricky ones. On the gateway I'm not going to have you necessarily do many or any tricky integration by parts. Okay? But it's still a value to work on and to do some, right? I mean, we're not just do this because this is what's on the test, right? That's more like doing the minimum. We'll do some other one, like we had a few in the homework here that go beyond that. And we still need to be exposed to that and see it and practice it some. Okay? But I'm telling you, for the gateway test, they're going to look like that. You see that? That's integration by parts. Okay? All right. So that's a small part of the gateway test. The bigger part of the gateway test is use substitution. All right. So integration by parts is this formula here. So if you figure out that it is going to be an integration by parts, then there are two parts. That's why it's named that. There's the part you're going to call u, and that's where you use that liate to help you remember what to pick for u. If you have a log function, you're going to pick that for u. If you have an inverse trig, you're going to pick that. Whichever comes first in liate of the function families that are in the problem, that's what you're going to pick for u. And everything else is the dv. Okay? Now, I want to do a couple of the trickier ones you had. Number 20. Here's number 20. Now, I've changed number 20 just a little bit. Okay, the number 20 you had, this was in the book now, right? The number 20 you had was what? It was e to the 3x, right? And then cosine 2x. Now, the only reason I don't want to do that is because I don't want to spend a lot of time today getting all caught up in that 3 and that 2 in there. Now, what's going to happen? Well, you know in an integration by parts, whatever you have for u, you're going to do the du, which means derivative, right? And whatever you have for the dv, you're going to do what? Antiderivative, because you have to go from dv to v. Now, whenever you do the derivative of, say, an e to the 3x, what do you have to do? When you do the derivative, kick out a 3, right? When you do the antiderivative of e to the 3x, you have to kick out a 1/3, right? If it's e to the 3x. If you're doing the antiderivative, you kick out a 1/3. Right? Same thing here. With cosine, when you do the derivative, you'll kick out a 2. When you do the antiderivative, you'll kick out a 1/2. And so when you go through number 20, you're going to have these 3's kicked out or 1/2's kicked out. And then you do the antiderivative again when you set up the formula. And then So you kick out another one, and then it starts getting real messy. So if you already went through that, that's great. That's fine. You know, good for you. But then something else really weird happens here too. And that's the part I want to focus on. So I don't want to get caught up in all the fractions and the other numbers in there. So I'm going to change it to this right here. So if you'd like to write this down this way as your number 20, that'd be just fine. Okay, because I want to focus on what happens. Now what we have is an exponential with a trig, right? There's no inside, there's nothing we could do to do a u substitution here. There just isn't any. So according to Liate, we have an exponential and a trig. Which of those comes first for our u? The trig, right? So we do sine x for our u, and our dv is going to be the rest, which would be e to the x dx, right? So we pick our u by Liate, the dv's whatever's left. And again, somebody mentioned this to me yesterday and said they like this because all they got to do is follow the rule, right? You just follow the formula, which is this right here. So it's going to be u times v. Well, we need v, I guess, here first. What is v? That's just e to the x. We don't have to worry about a plus c, okay? We do the antiderivative. We'll put that on at the end. And over here I need a du. So what's that? Cosine x dx. Okay. So follow the formula, which is u times v. So that'd be e to the x times sine x minus the integral of v, which is e to the x, and then du, which is this. Now, by the way, this is another thing that came up. Whenever you're doing integration by parts, you're writing down you want v times du. If there would have been a 3 in front of this, we don't divide that 3 over. You know, in u substitution, we do that a lot, right? If we have a 3 here, a lot of times we divide that over, right? Because it's not in the function, so we want to get out of it. In integration by parts, you never do that, right? Because you're just following the formula. You're taking u times v and then minus the integral of v times du, whatever's here. You don't want to move that over there. Then you've got 1/3 du. Our formula doesn't ask for 1/3 du. It asks for v du. So if you ever get a 3 or you get something over here on your du, we don't divide that over like we do with u substitution. Okay, so make sure you understand that. All right, so now we got this. Oh, geez. What's supposed to happen when we do integration by parts? And we get to here. Supposed to what? Well, the whole idea in all these techniques is to turn our original integral into some integral we can easily do, right? Now, when we say easily do, what we really mean is just a basic antiderivative would be nice, right? Something where we could just do a basic antiderivative, but it wouldn't have to be that. Matter of fact, we're going to do a problem in a minute where we've got an integral that we start with here, and when we get to here, we have to do a u substitution to do this integral. I mean, that's just the way it goes. I mean, but the idea is we turn our original integral that we have no way of doing, we turn it into a new integral that we do have a way of doing. Well, we hope most of the time it's just going to be a basic antiderivative, but it's possible that we get a new integral that we need some other technique on. Okay, well, it turns out that on this one, we need what? What technique do we do that's got two different function families and nothing we can do a u substitution on? Integration by parts. I mean, look at this. It looks just like our original almost. This needs integration by parts again. So, what's that? That's what the original needed too. The original ended, this one ended up. Okay? So watch what happens though. Now, there are some other ones where you have to do integration by parts twice. When you do integration by parts twice, it ends up working. And then you're done. But let me show you something, but I'm not going to give you that on Monday either. But look what happens here. So now what I do is I'm going to do u again. I got an exponential and a trig. So again, we're going to let it be the trig. Okay. Now I know I already used u before, but I think I can use it and not get confused here. And then the dv is what's left, which is the e to the x dx. Okay. And then the du here would be negative sine x dx. And the v would be e to the x again. Okay, now I'm not going to forget about this over here, so I'm being careful to line this up here. Matter of fact, let me change colors. So now I'm going to do my formula. This minus is still there, so I'll bring that in later. So now my formula says u times v, which would be e to the x cosine x, minus the integral of v du. Now, see, here's my point. This negative, I don't want to divide that negative over there. We want it stays there. We want the integral of v times du, and here's du right here. So we need negative. Now I can turn that into a plus then. That negative will turn that to a plus. And then this would be e to the x sine x dx. Oh, geez. What do you notice? It's the same thing we started with. But that's actually a good thing. Well, sure, yeah, this endless loop, basically. No, here's what we have. Here's what we have now. Let me go to a new page. So what we have is our original integral. Write this down. Here's what we have. We have the integral of e to the x sine x dx is equal to, let me come back. What do I got? I got this. So I got e to the x sine x. It's going to be long, so I got to say minus all of this, right? So it's going to be minus e to the x cosine x, and then minus, because I have to distribute that, minus, right? Minus the integral of e to the x sine x dx. Are you with me? Why is there two right there? This should be sine x. Right? But that was this. Okay, so I started with this, right? I started with this. This is equal to this minus this, right? So and that's why there's another one right here, because it's that one right there. So all I did was write that out. I said, okay, here's what I started with, and that is equal to this minus that. And that's what I have on this page right here. Any ideas? No. Let's call this the red thing. That's what I'm trying to find is the red thing, right? I got another red thing over here. No, you don't cancel. This is what I do with my algebra class when we solve equations. I put a wall here. I call it wall problems. Do what? What do you mean put them together? Add this red thing over to this side. What do I have? Two red things. So I have 2 e to the x sine x dx equals e to the x sine x minus e to the x cosine x, and then what? Divide by 2. And there's my answer. There it is. Okay? Now, why did that happen? Well, it happened because e to the x is its own derivative and own antiderivative, and sine and cosine just bounce back and forth between each other when you do derivatives, right? So when you did it twice, you went from sine x to cosine x, and then did it again, you went back to sine x, and you ended up with the same thing. Anytime you got a sine cosine paired with an e, this is what's going to happen. You're not going to have to do that in the derivative. For my, I would have lost them way. And then when I lose them, they're gone. I mean, I can't get them back. So, yeah, that wouldn't be good. What they would probably hone in on is the fact that we spent, if you look at this problem, there wasn't a single number appeared until right there. Right? They would have looked at that and said, that isn't math. There isn't a single number anywhere. I just hear number 20. Right? And then that 2. I mean, that would have freaked them out just that right there. So, all right. So that's one thing that can happen on integration by parts. Okay, this repetitive thing. There are some where you can do them twice. Now, we did this one yesterday. We did this one as our very first example. And what happened was the u was the x, so the du was just dx, so our integral is just e to the x, which made it easy. If this would have been an x squared, then our new integral, so we'd have had x squared times e to the x, our new integral would have been x times e to the x. The power would have decreased by 1. So we'd have had to do it again. But then the second time, we'd have had just an integral of e to the x, and then we'd have been able to do it. We'd have been done. Now, if this be x to the sixth, you have to do it like 6 times. You know, I mean, I wouldn't give you one of those, but that, I mean, you know, that's what could happen. That's another thing that could happen in integration by parts. Okay, let's talk about number 19. These are all ones that were in your book, okay, on the integration by parts section. Okay, and then we add in the definite integral, which means we got to then stick that in there at the very end too, the f of b minus f of a part. But let's talk about what happens on this one. So we've got an algebra and an inverse trig. So according to Liate, we do what? We use the inverse trig for our u. So we go arc tan x. And the dv is everything left, which would be the x squared and the dx. I'm not going to worry about the -1 and the root 2 over 2, you know, until the very end, and I'll put those in, do f of b minus f of a. All right, so the du is what? What's the derivative of arc tan? 1 over 1 plus x squared dx. And the v, antiderivative of x squared, 1/3 x cubed, and you know, don't worry about the plus c till later. All right, so now I end up with, so I got u times v, so that'd be 1/3 x cubed times arc tan x minus the integral of v du. So it's these two things put together, right? V and du. Now let's think about how we're going to put those together, because how you write them makes your integral much easier or more difficult. So 1/3 I can put out in front, right? And then what about the x cubed times this fraction? Put the x cubed on top. So I'd have x cubed over 1 plus x squared and then my dx, right? So when I put v du, when I put that together, I've got that. All right, so the whole point of u substitution or integration by parts is to change our integral that we have originally into a new integral that we can work. Hopefully one that's just a basic, easy antiderivative, and I told you the ones I give you on the gateway will be that. But it might be not that, right? It might be we have to do some u substitution or some other technique. Well, right now that's the only other technique we have, okay? And that's the only one we're going to get. So this is a u substitution. Now, the reason this is a valuable problem to go through is I wouldn't give you one this hard on the gateway test as far as an integration by parts and then a tough u substitution all inside the same problem. However, I might give you this integral on the gateway test as a u substitution problem, right? And it's got a something in it, a little trick in it that we haven't done yet, right? I don't think, unless you've done it on one of the problems in the book and haven't asked about it, but I know in class we haven't done it. Okay, so let's forget the 1/3, let's forget all this other stuff, let's just focus in on this guy right here. So what would be some options for us to do here? Now, let u be x cubed. Letting u be something on the top is often not a good idea. It can be. I know why you're going there, because you're thinking of the du, right? You're thinking of the du would be x squared. Unfortunately, is there an x squared dx here? No, it's on the bottom. It's a 1 over 1. You know what I mean? It's not quite that, but so I know where you were going with that. Because what's the only other option? Let u be the bottom. Now, if you let u be the bottom, if you let u be 1 plus x squared, what's the du? 2x dx. Now, do we have an x dx here? Kind of. That's exactly right. We do have an x dx here, because we can take this x cubed and we can make it x squared times x, right? So it's really an x squared times x times dx. So we can peel apart that x dx. We can do that. And so I might, well, give you this problem just on this problem itself right here on the gateway test as a u substitution. Okay? So that's something we can do. So let's go ahead and do it. So we're going to let you, now I know I already used U for stuff up here, but I'm not using it down here anymore, so I'm okay. Or you can use W now if you want to, whatever. I'm going to use U again, so it's a different U than what we did up here, but we're done with those, so I don't care about it. So I'm going to let U be the 1 plus x squared. Okay? And then the du would be 2x dx. Now here, I'm doing U substitution. Now, I'm not doing that integration by parts thing. So I can go ahead and divide that 2 over there, because I don't want it. I have an x dx in there, so I want my x dx here by itself. I don't want the 2 there. So I'm going to move that 2 over here. All right, so I got x dx. All right, so now how do we do a U substitution? We come over here and we write our new integral. So now the 1/3, I can probably deal with that later. So I'm not going to mess with that. I'll just remember that's there. I'm just working with the integral right now. Okay, so what's on the bottom? That's U, right? So I'm going to circle that. I've taken care of that. And then right here is my x dx, right? And what's that? What's x dx? 1/2 du. So 1/2 and the du I'll put there. And then what's left? There's an x squared there. But what's x squared? See that? But really regret never saying that. Okay, u minus 1. We solve, in this case, for x squared. X squared, we got this extra. Remember we talked about having an extra x sitting out there? Well, if you have an extra x, we can solve for x here. Well, in this case, we got an extra x squared, but that's okay because we can solve for x squared very easily. X squared is just u minus 1. So for the x squared, we can put u minus 1. Now, have we not dealt with those before? What do we do with that? Split it up. So we got a 1/2, and we got 1 u over u, and then minus 1 over u. I'm going to leave it like that because that's an ln, right? So now my antiderivative, I'm going to put 1/2 on all of it. So I'm going to have 1/2. What's the antiderivative of 1? U. And I'll put a 1/2 on this. Antiderivative 1 over u. Natural log of u. Okay, and remember u was 1 plus x squared. So this is 1/2 1 plus x squared minus 1/2 ln 1 plus x squared. As if there's not enough going on here. Is 1 plus x squared ever going to be negative? 1 plus x squared never is going to be negative, so we don't really need the bars. Leave them there is fine. Okay? All right, now let's put it all together. So starting all the way back here with the blue, we got 1/3 x cubed arctan x. Now we're going to distribute this minus 1/3 to what I have down here. So that's going to be minus 1/6 1 plus x squared, which I could even distribute that, but I don't need to. Minus 1/6 ln 1 plus x squared plus c. And I'm circling it because I'm going to stop, but actually I shouldn't stop because it's a definite integral. Oh, man. I mean, this is everything in one problem. It's all there. Okay? Because, yeah, then you would write bracket and you would go here to here. These are the ones the college professors love. Man, they give you the algebra, you got algebra, you got all this stuff. So, you know, you're cussing me now, but a year from now you might be saying something different. Maybe not. Probably not. But, okay. All right. So, yeah, and then you would go in there and you put square root of 2 over 2. Now, the arctan of square root of 2 over 2, oh, that's not even a nice one. That's like root 3 or something. No, it's got to be manual. Arctan of 1 is pi 4. Or root 2. All right. Yeah, there you go. All right, so anyway, not going to be that kind of nasty thing there. But what this points out is a situation where, again, integration by parts, because we got to mix. There's nothing here. Think about this now. There's nothing here that would be a U substitution. There's just nothing that when you do the du, it would take care of stuff that's there. It's a mixture of two different things, just like I showed you back on this page here. Okay, it's a mixture of two different types. So you use the Liate to start it. But what happens is you get a new integral that hopefully is easy to do, or at least you can do. Well, we could do it, but it was a tough one. It was a tough u substitution one. So it's really a challenging problem. Okay, let's go to 31. Now in 31, they gave you kind of a hint as to what to do, and this is the reverse. This is the reverse. In the one we just did, we did integration by parts, which gave us a new integral, which we could then do u substitution on. What they're telling you here is to let u equal x squared and then do integration by parts. So they're kind of telling you what's going to happen ahead of time. But let's pretend they hadn't told you. You would look at this, I would look at this, and I would say, well, it's a mixture. It's got x, it's got e. So that sounds like integration by parts. However, I got this inside, right? When you got an inside, that makes you think of u substitution. So if you said, well, if I let u equal x squared, then the du is going to be what? 2x dx. And then so you would ask yourself, do I have an x dx setting there? Kind of, just like the last problem we did. I've got an x cubed dx, but there is an x dx in there. I could make this x cubed into an x squared and an x. And that's what we're going to do. So the 2, of course, is not in there, so I'm going to divide it over. Because we're doing u substitution right now. We're not doing the integration by parts thing. So I'm going to give myself a new integral here. So let me, so x cubed we're going to think of as x squared times x, right? So this part here is just going to be e to the u, right? That part's going to be e to the u. The x and the dx is going to be what? 1/2 du. And what that leaves me with is an x squared. And what's x squared? It's u. Now what do you have? Can we do this integral? We can't do those individually, right? We can't do that antiderivative, that antiderivative. We can't do it. No, that is this guy right here. That's an integration by parts. That's a mixture of two function families, no substitution that we can do. Now, problem is, to do integration by parts, I'd like to use u and v because that's what my formula is. So let's change these to all the w's. Let's make these u's into w's. That's pretty easy to do. So now it's w, it's w e to the w d, yeah, w e to the w dw. Okay, and so now we want to do integration by parts. So I got an algebra and I got an exponential. So we let u be the algebra, right? That comes first in Liate. So we'll let u equal w. We'll let dv be the e to the w dw. So du would be dw, or just 1, but right? And then v is just the antiderivative of e to the w. Antiderivative, that's just the e to the w. Okay, so according to integration by parts, I'll go ahead and bring the 1/2 along here. So we would have, well, I'll remember the 1/2 at the end. I'll bring it in at the end. So u times v, so that'd be w e to the w minus the integral of v du. V du would be e to the w dw. Oh, that's an easy one, right? So I get w e to the w minus e to the w plus c. Now I can't forget I got a 1/2 in front of all that. Okay? And then I got to take w out and put x squared back in its place. So I've got 1/2 x squared e to the x squared minus e to the x squared. Oh, that's a 1/2. That's got a 1/2 on it too. And then plus c. C times 1/2 would just be another constant. Okay, so those two problems just showed, you know, the reverse situations, right? I mean, we had an integration by parts, and then we needed a U substitution at the end. We had a U substitution. We started with a U substitution, and then it ended up being something that needed integration by parts. Okay, it's good practice. Each of those individual pieces was good practice. They're not going to be any on the gateway test where you have to put both of those together. Okay, you're going to do a U substitution and you'll get your answer. You're going to do an integration by parts and you'll get your answer. Okay. And you got this. I don't think so. I doubt. I don't care if you show me. I don't believe. All right. Tell me what you did. Quick.
Well,
You let U equal to x cubed.
I see what
Oh, did you go the other way?
I got the answer down there.
Did you let U be the x cubed? Or did you let U be the e to x squared? You know what you did? Well, according to Liate, algebra would come before exponential.
Yeah.
The problem is there an antiderivative of this right here? There is no antiderivative e to the x squared. When you have an x squared in there, you can't do it. There is no antiderivative of that. Now, if you flipped them and let that be there, then I don't think so. I know, Ryan, I'll look at it, but I don't think it.
Well, yeah, it doesn't work because I had u equals x squared.
And then did dv.
Yeah, something. I don't know. I somehow managed to get the same answer.
Oh, you know, if you let u equal, the rule is you let u be something, and then the dv is everything else.
Yeah.
So if you split this into an x squared and an x, you could let u be the x squared, and then the dv would be x e to the x squared. Which, when you go from dv to v, you have to do the antiderivative, right? Well, you actually could do an antiderivative of this with its own u substitution right there. Because if you let u be that inside, you'd have your x dx right there. So it's possible, maybe. Well, I don't know.
I don't know.
I'd have to finish that. Is that what you did?
No, well,
That's not what you did.
Well, I just lost an x in there.
You
I
lost,
don't know if
yeah.
I wrote it down.
Well, sometimes if you just drop stuff out that's inconvenient, sometimes that's nice too. But unfortunately, not correct. Yeah. All right. What else? How about the LH packet? Let's go to some straight U substitution ones. If somebody's got one they want to see here. I mean, I want to give you some practice time. I've got some review ones I'm going to throw up here, then give you time to work, and then throw up the answers to see how you did. And just kind of simulate the gateway test a little bit. We're going to do that a lot tomorrow, too. Anybody? Anybody got one on the LH? Well, let me show you one that somebody in the other class came up with yesterday. I think this was in the book. It's x plus 4 over 1 plus x squared dx. This is what somebody asked yesterday in the other class from page 340. I'm not sure which number it is. It's number 41, actually. It's number 41. Say that loud. Okay. Now, you're exactly right. But let me talk about, before I do that, there's another one really close to this one. It's number 43. Number 43 looks like it. It's this problem here, and then inside of here it's got x squared plus 3x plus 5 all to the fourth or something, I don't know, something like that. Now, what would you do on this one? You be the bottom. Inside of the bottom. Inside bottom. And the nice thing about that, if you let u be the inside, what's the du? 2x plus 3, which it happens to be this, which is a really nice u substitution. So here we have something that looks kind of like this one. And we didn't have to split it apart or anything. It just worked really nice. However, on this one, if you let u be the bottom, what's the du? 2x dx. Is there an x dx here? No. Now, we just got done talking about one that had an x cubed, and we said there is an x dx in there because you can break the x cubed into x and x squared. The problem is you're breaking that as factors, multiply. And that you can separate out the x dx and the x squared, right? But you can't do that with a plus. This is like x plus 4 times a dx. You can't just pull out the x to go with the dx. There is not an x dx here. So actually what you can do, and what you need to do on this one, is split this, and this is another little thing here that we have not seen before. Remember, we can't split a denominator though, right? You cannot split a denominator. So the 1 plus x squared has to stay together. But I can split this into these two here. Now this one would be a nice u substitution, right? Because if I let u be the bottom now, if u is 1 plus x squared, what do you say the du was? 2x dx. Well, there's your x dx right there. That's going to be nice. What about this guy? Pull that 4 out in front and pretend there's a 1 right there. That's arctangent. That's arctangent. Right? This 4 can just come out in front, and there's a 1. That's arctangent. So this one is just, you don't need any u substitution or anything. This is just going to be 4 arctangent, right? And then this one's going to be whatever you get when you go through and do your u substitution here. It's going to be a natural log, I think. So there's another thing to look for, right? You let u be the bottom. You got 2x dx. There's not an x dx there. There kind of is. If that 4 wasn't there, well, since there's a plus, we can split it into 2 separate intervals. And again, another thing you always look for is that 1 plus x squared, which is arctangent, or the square root 1 minus x squared, which is arcsine. Whenever you see those on the bottom, you're thinking, hey, it could be an arctangent. Now, in this first one, it's not, but on this one, it is. Okay? So that's something to think about. So that was number 41. So I thought that was a good question somebody asked yesterday. So you notice, again, the more you practice, the more you run into these little kind of tricks or whatever that show up, these little things that come up. And so you see them and practice them. If you see them again, you should be better. All right, let's go to the website real quick. Let me show you that stuff again. This is on because I think over the next 2 or 3 or 4 days before Monday, I think this is someplace you ought to spend some time. Under the web links, because we're about out of LH problems. There's some more there. The book, that page 340, that's going to be a good source. But if you go to web links and you go down here to antiderivative practice, and again, the link to my website, this is where the videos and stuff are. If you've never been there, that seems crazy. But if you've never been there, you can carneycats.com. On my homepage on Carney Cats, it's a link to there. But here you've got right here where it talks about integration. You can review and practice your integration by part skills here. The flash animations are really cool. I don't know about that, but here is a few of them, and I'm not sure how well this works. We'll see. Been here a few. So here you have an algebra and a trig, right? Here you got an algebra and an e to the x. Here you got an algebra and a log. Okay. Here you got an algebra and a trig, and then this is that one we talked about that's nasty, right? The exponential with the trig. That's the one that cycles, and then you got to kind of do it. So I wouldn't worry about that. But these first couple are pretty good ones. Now it says solution using Flash. Click to continue. So there's your u and your dv. There's your du. There's your v. Now they actually write the v. They say, hey, you're going to do that antiderivative. So then they get that. That's where you kick out the 1/4. Okay. Click to see why. Okay. Whatever. Who cares about that? Then they give you the thing there. And then they got u. They show you, okay, there's u times v minus the integral of v du. Okay, you get this. Now you're doing that. You're going to kick out that 1/4. Okay. Then I would ignore the y's most of the time. Okay. Anyway, you just kick those out and they give you the final answer. So those are really cool. All right. So anyway, so that gives you some problems. Then down here it says some drill problems using integration by parts, like examples 1 through 4. Those would be the ones I would stick with on 1 through 4. Okay. And so if we say using Java, let's see if how that works. Java needs your permission to run. Okay, I was afraid of that. Change problem. Yeah, so I don't know. I don't know if there'll be a lot of other ones, but again, integration by parts is a fairly small part of what's on there. You can kind of make up your own too. Let me see if there was another place. It covers substitution, not integration by parts. The cow one. I can't remember if that we didn't like that one that much. Integration, indefinite integrals. Substitution, integration by substitution. I don't know that didn't really have any integration by parts on it. So there's not a lot of good places for integration by parts problems other than what we were just talking about. There are a few there. If your computer, if Flash will work, I have to mess around with that to see why mine, how I do different browser would probably work better. And so it just gives you some more examples. So there's a place for some integration by parts. I'm also going to give you some other things. Let's do this right now. Let's go to. All right. Oops. Don't look. All right. Let's do. Okay, there's 3 problems right there. Okay? Let's go ahead and take a little time and work on those 3. And then we will check them. Work together with somebody if you want to. Work together with a partner or whatever. If you're watching the video, there's now going to be about 10 minutes of silence. So you can fast forward. Where? This is -6. This is a 7 here at the beginning. Yeah, this is a 7 here at the beginning. Okay, 7 at the beginning, -6 at the end. This is what I would call your basic antiderivative. Now it's got some tricks to it, with the 4 inside you got to deal with here. You probably need to distribute that first, right? So this is one of those things we said you might have to do a little simplifying, whatever, but then it's just your basic rules from page 333. Now, I've got about 10 of them on here. And whatever ones we don't get to, I will post on our class website under today's assignment. And it's got the answers. It's just a PDF file with the answers worked out too. So that'll be part of your homework to try them and then check your answers. Okay?